So I'm going to do my best to explain the Hardy-Weinberg equation today. And what this is a little equation that's going to show us the different alleles in a population. Now, what's going to happen is if let's say that we're talking about eye color, for example. If you have a dominant eye color and a recessive eye color, we can see the phenotype, what's actually physically being expressed by looking at the eye color. So we can see here what I've done is I've taken black paper clips to represent a recessive trait, and I've taken these little silver guys as a dominant trait. So we can think of this as blue eye color, and these guys as like a dark eye color, like a brown or a green. Okay, and so this is going to dominate. So what you might have is a little guy that looks like this. Okay, he's got a recessive and a dominant. But since this silver guy is dominant, what's really going to show up is this silver guy. Kind of like this dark eye color is going to show up. It's going to mask that allele for that recessive trait. So in order to have a recessive trait phenotype to actually be expressed, you have to have both of these little guys. If you have a dominant one, that's obviously it's going to dominate. That's why they call it the dominant gene. So what we're going to do is we're going to figure out exactly how many little black paper clips. I don't have them all displayed in front of you here, but I have 100 different groups, and I've got 9 of these little recessive guys. So anytime we do a Hardy-Weinberg equation, we always want to find the recessive traits. We want to find the two small q's is what we're actually looking for, p and q, and so we're looking for q squared. So I have 100 groups total, and out of that 100 groups, there's 9 recessives. Okay, so here's our 9 groups, 1, 2, 3, 4, 5, 6, 7, 8, 9. What we're going to do is we're going to count that. Our total groups that we had, there was 100 people that we looked at, if you will, okay? With different eye colors, if you want to think of it that way. There was 100 people, and out of those 100 people, 9 of them express this recessive trait. So when we divide that, 9 divided by 100, we're going to get 0.09, or 9%. So 9% of these groups, 9% of these little paper clips were the recessive trait. They were the black paper clips. So what we want to do is we want to call this our Q. And this is actually going to be Q squared, because there's 2 of them. So a Q and a Q. Q squared is 9%. So when we want to solve for Q to figure out what just Q is, because what we're looking for is this equation, this initial equation of P plus Q equals 1, or 100%. That's what we want to find. So by doing this equation here, where we took 9 divided by the total, we found Q squared. So if we want to solve for Q squared, we have to take the square root of Q squared to get rid of this 2 here. And so you have Q equals square root, and then we have to get square root over here, just do that to both sides. So you get the square root of 0.09, and I take out my calculator to make it easier. 0.09, oh goodness, second square root 0.09 gives me 0.3. So our Q, let me move our little guys here, our Q is 0.3. or 30%. And this is the probability that if I put all these paper clips, all the silver ones and all the black ones, and I separated them into individual paper clips and I put them in a bowl, what are the odds that I'm going to grab a black paper clip? 30% chance that I'm going to grab a black paper clip. So what is the chance that after I grab a black paper clip, I grab another black paper clip? Well, there's way more silver paper clips, so the odds I'm going to do it twice pretty low, 9%. But the odds that I'm going to do it one time, 30%. So what are the odds that I'm going to grab a silver paperclip? Well, those odds are going to be pretty good. So if we know with this equation that P plus Q equals 1, and we know that our Q we said was 30, well then we can just subtract 30 from 100%. And that's going to be 70%. So our P is going to be 0.7, or 70%. And if we wanted to find our P squared, I would just square 7. Probably don't need to do this, but we can square our 7, and we've got 49. 0.49 is our P squared. We'll put it here. P squared equals 0.49. So, the odds that I'm going to grab one silver paperclip, pretty high, 70%. What are the odds that I'm going to grab another one? Well, that's going to be 0.49. The odds are going to go down a little bit for me to grab them both back to back. So, this is really helpful because we can see exactly what the probability is that I'm going to get one Q, what's the probability that I'm going to get two Qs, what's the probability that I'm going to get a P, and what's the probability that I'm going to get two Ps. But in nature, if we're talking about eye color again, I want to know if the person with green eyes potentially has that allele for blue eyes, because their children could still end up having blue eyes. Just because they have green eyes doesn't mean their children can't have blue eyes. So we can't observe just by looking what alleles that they have, but with the next step of the Hardy-Weinberg equation, I will show you how we can find the heterogeneous using these numbers. Okay, so now that I've cleaned this up a little bit, let's go back and see what we were talking about. We found that our P is 0.7, or 70% chance that I'm going to pull just one of these guys. Our Q was 0.3, or 30% chance I was going to get one of these guys. Our P squared was a 0.49%. 49% chance that I was going to do it twice. The odds are against me more so than they were up here. But the odds are really against me to do it here. What do we say? 0.09, 9%. Then I'm going to grab two black ones. That's pretty unlikely. But what I want to know, what are the odds? I'm going to get this guy right here. A silver and a black one. So we said P plus Q equals 1. Well, what happens if we square both of these guys? Well, I'll do it once so you can see what this looks like. I think you should all be pretty comfortable with doing this though. P times P is P squared. P times Q is a PQ. And a Q and a P is a QP. What's really important about this, what this is saying, is let's say from the dad I get a P and from the mom I get a Q. What if I get a Q from the dad and I get a P from the mom? What does that come out to be? Well, it comes out to be a P and a Q, either way. So it doesn't really matter. It doesn't matter which one you get first, because the dominant one is going to dominate. Doesn't matter who gets it from where. So really, instead of a PQ and a QP, this turns into is a 2 PQ. And then Q times Q is Q squared. And then 1 squared is still just 1. So we can figure out what this is. This is our heterogeneous sample. This is our sample with, oh, this guy here. This is these guys. And this is this guy. So, review, P squared was 0.49. Q was 0.09. This is going to equal 1. So our p, not our p squared, just our regular p, if we remember the square root here, this was 7. And the chance that we were going to get just one q, there was a 30% chance. Okay, so we can do it like this. We'll say 0.7 times 0.3. And then we're going to multiply this by 2. Because there's two possibilities, a PQ or a QP. So again, pull out our calculator. 0.7 times 0.3 is 0.21 times 2 is 0.42. So the probability that when I randomly grab a paperclip from the bowl and I get a silver one followed by a black one, or a black one followed by a silver one, that probability is 0.42. And you'll see that this works out. I'll prove it. 0.49 plus 0.42 plus 0.09 equals 1. And that's perfect. That's exactly what we want. And that is the probability that this is going to happen. So, to put this to the test, I'm going to put in my 100 groups. And I'm going to separate them. I'm going to grab randomly. And then I will see how close we actually got. Alright, so here is the final results. So, what we ended up having is 4 recessive pairs. So 4%. We had 44 dominant pairs, and then 52 heterozygous. So that's pretty interesting when you look at our numbers, what we were expecting to get. It's pretty close. So they both equal up to 100%, because obviously when you reach on the bowl you're going to grab a paper clip, so there's a 100% chance you're going to grab something. But it's really interesting. So if our population was even bigger, we'd get even closer to these realized numbers. So that's one of the things with Hardy-Weinberg equations, is that your population has to be pretty large. So you could say that this is starting to get out of Hardy-Weinberg equilibrium. Let's say it just happened, 4%, I only got 4 of these things, so it could have happened where I didn't have these guys at all, right? And so it's starting to fall out of Hardy-Weinberg equilibrium. And so that's one of the rules. There's got to be a large population. If this was an island and there was only 100 creatures for us to choose from, then it may not be in Hardy-Weinberg equilibrium. It's got to be a pretty large number for this math to actually work out. But as you can see, just with 100, we got pretty close. So to go backwards from what we did, this is what you would see in your environment. And you couldn't really count these guys because you can't tell these guys apart. These guys are going to look the same. The ones you can tell apart are these guys, this 4 down here. So you could say, from looking at this information, out of 100 is 0.04, is 0.2, and so 100 minus 0.2, our p would be 0.8. A p squared of 0.64. And then if I did 0.2 times 0.8 times 2, we'd have a 2pq. Let me get this out of here. 2pq of 0.32. And there you go. That's Hardy-Weinberg equations when something is in Hardy-Weinberg equilibrium.